Okay, welcome to part 4 of Math3611. Right now we're going to talk about topological spaces. Quite a big topic, so a lot to cover here. So what we've done before, we've mainly been dealing with metric spaces. So that's when we have a set equipped with some notion of a distance. But right now what we want to do is we want to move our focus to convergence rather than just distance, right? So if we care about convergence, what we're going to do now is we're going to make a topological space. And what that is it's a set, a set equipped with this thing tau called a topology, which is the collection of open sets of X. So in metric spaces, open sets were defined by the metric, but now we're defining open sets without the metric. And so, like, this is our choice now. An open set, we decide what counts as an open set, and that defines our topology. Okay, so this is what a topology needs to satisfy. So it's called a topology if it contains the empty set and the whole set. It's closed under possibly infinite union. And closed under finite intersection. And this is equivalent to just saying that V1 intersect V2 is also in tau. Because if you can do it for a pair, then you can do it finitely many times. So the elements in tau are called open sets. And yeah, this pair is called a topological space. If you want to, I don't know if it's an easy way to remember, but it is a way to remember. If you just think about our normal open intervals in R, these satisfy closure under infinite union and finite intersection. So here are some important ones. So we have the discrete topology. This is the entire power set, so it's the largest one. The coarse topology, which is just the empty set and the whole set. Remember, that's one of the conditions we need. So this is the smallest possible topology. There's a metric topology, which is just defined by the metric here. So it's not exactly just the open balls in that metric, but it's built upon them. Cofinite and co-countable, these are a bit weird. So the co means the complement. So cofinite means the complement is finite. So yeah, x take u is finite, x take u is countable. And of course we need to just manually add the empty set. And then the subspace topology is if you have a subset of a topological space, then you kind of reduce the topological, you reduce the topology to just S. So you have the original topology and you intersect it with S. So what that would look like maybe is, okay, so if you have, if this is your set X and your topology, so a topology is like a way of writing down what all the open sets are. Actually, maybe there's a better way to say this. Let's say this is X, and then your topologies look like this. So these are our open sets. Then if I make a new set, a subset, let's say this is the subset S, then the topology on S will just be defined by these open sets. Okay. So here's just some definitions. This isn't really a theorem, it's more of a definition. Closed if the complement is open. So that's similar to what we had before. And we can also denote the closed sets as C of x, and it satisfies some properties. You think of this as it's just the set of V complement where V is in tau. And what happens is, well, since the empty set and the original set were in tau, their complements, which are the empty set and the whole set, are also in the closed set of closed sets. And then now it's closed under infinite intersection and finite union. I should say possibly infinite intersection. So yeah, this is flipped from open sets just because, I mean, closed sets are like flipped versions of open sets. And again, you can remember this if you just think about how closed intervals in R work. So here's some more definitions. So an open neighborhood of X is an open set. So remember, an open set's just anything inside our topology. So it's an open set that contains X. And a neighborhood, so that was an open neighborhood. A neighborhood, all it needs to do is contain an open neighborhood. And the collection of neighborhoods is called NBHD, neighborhood. We can then define the interior of Y by the set of all Y such that there's a neighborhood inside Y. So remember how with metrics, it was the set of Y in Y such that there exists like a ball centered at Y with radius epsilon inside Y. Here we're replacing arbitrarily small balls with, I guess, arbitrarily small neighborhoods, although there's not necessarily that notion of arbitrarily small neighborhoods. So with the topology, we're now looking at the set of Y such that there exists a neighborhood with Vy, not element of, as a subset of Y. So that's just what they wrote there. But there's a better way to write that. So if we think of this as X, sure, you can check each individual point that there is a neighborhood in it, or you can just take the union of every single open set inside. Right? So if you take all of these, I'm drawing them as circles, but they don't necessarily have to be. If you take the union of all of them, so union of all open sets in Y. Oh, sorry, I should have labeled that as Y, not X. Yeah, then you take the union of every open set in Y, and you should get the interior. And then we can think about how this generalizes to interior points of, generalizes the concept of interior points on metric spaces. I kind of talked about it already. And yeah, the interior set is an open set. Okay, some more definitions. These are just similar, well, like, they're exactly like we know already. It's just now the interior is defined in a topological sense. But apart from that, everything's the same. Okay, the closure. So the closure, we can think of it as, in some sense, it's the smallest closed set containing Y. Actually, that's written here. The closure of Y is the smallest closed set containing Y. So that means if we take the intersection of all closed sets containing Y, then we're all to get the smallest one, right? And so yeah, and a part of this is that closed sets are, well, okay, if a bunch of sets are closed, you can take the infinite intersection of them and it will still be closed. And hence, this possibly infinite intersection is also closed, and it's going to be the smallest one. There's some other characterizations. Let's just see. Yep, intersection of them all. I just showed that was equivalent to the smallest closed set. I didn't show it, but I explained the intuition behind it. Union of interior points and its boundary points. So that's from up here. And the closure of Y is Y with its limit points. Okay. Here's... Okay, yeah, so this first section here is how we define convergence in a metric space. It was that, okay, I think a better way to say this is if a sequence converges to this point here, then what that means is that we can always, for all epsilon, so that means epsilon can be as small as it wants, I can draw an epsilon bore around this point, and my sequence is eventually inside it. So this point is x, x epsilon, the sequence should eventually be inside it. So there's an n such that if n is greater than n, then it's within the bore. So we're going to generalize this to neighborhoods. So remember, with neighborhoods, we generalize these bores to arbitrarily small neighborhoods. Okay, that's not exactly rigorous, or like that's not a perfect characterization, because sometimes it can't be arbitrarily small, but it's good enough for what we need right now. For convergence in a topological space, for every neighborhood of x, so that means for an arbitrarily small neighborhood of x, we can find, well, xn is eventually in that neighborhood. So that means, just like before, but instead of using a bore right now, we're just using any neighborhood, and that means the neighborhood can be as small as you want. Then xn is eventually in V. So there's an n such that for all n greater than n, xn is inside the neighborhood. And I think that's what they're doing here. Yeah, so a sequence converges to x if for every neighborhood, so you can see for all v in neighborhood of x, there is a k that can depend on the neighborhood, such that beyond that point, my sequence is inside the neighborhood. So yeah, k can depend on v, and just a note, uniform convergence isn't really defined here, or like it's not really defined on the topological space, just because it's not that useful. Okay, before we look at convergence, I just want to reframe this in a, I think it's a much nicer way, but it only works, okay, the intuition you can kind of carry everywhere, but it doesn't work strictly all the time. It just works whenever you can apply it. So xn, I'm going to use a bit rough notation, but I just hope it's easier to understand this way. A sequence converges to x if xn is eventually in the smallest neighborhood of x. So remember how it said for all neighborhoods that this function eventually has to, that this sequence has to eventually be in the neighborhood. So I'm saying that if there is a smallest neighborhood, then xn eventually has to be inside it. But of course, there's like an asterisk associated with smallest neighborhood, because we don't know if it exists. If it doesn't exist, then there's a bit more work to do, and it's a bit annoying. Okay, so let's move on to here. I can give you a second to think about this. What values do these sequences converge to, if any? Okay, hopefully you've had a think. So for 1, yeah, we can get rid of this for now. For 1, I'm going to use my intuition, and just to remind us what that was. I need to be eventually in the smallest neighborhood of x for it to converge to x. Okay, so that means if I want to converge, let's just check all the values it could converge to. Since x is just 0, 1, does it converge to 0? Well, let's try to answer that. What's the smallest neighborhood of 0? Well, it's going to be the singleton. Is my sequence eventually always 0? No, because xn, what's the best way to write this? I'm trying to say that there's always a 1 if you want to go far enough. I guess I'll say for all n, for all natural numbers n, there exists a k greater than n such that is greater than or equal to, such that xk is equal to 1. And importantly, this is not in the singleton. So in your proof, it would be, it doesn't converge to 0 because there is a neighborhood of 0, which is this. Oh, sorry, there is an... okay, let me quickly fix something up, which is, I mentioned smallest neighborhood. Here I can add the qualifier smallest open neighborhood, just because they're going to be the same thing, but it's a lot easier to think about. Yep, so this is our smallest open neighborhood containing 0, and it's not eventually, the sequence isn't eventually inside this set, so it does not converge to 0. Okay, how about does it converge to 1? Well, what's the smallest neighborhood containing 1, or smallest open neighborhood? Well, it's going to be just x, and obviously the sequence, I'll just say xn, even though they haven't defined it, xn is eventually in x. In fact, we don't even need the eventually, xn is just always in x. So it does converge to 1. And your proof for this would be for all neighborhoods. Okay, I'll just write this out nicely. Let v be in the neighborhood of 1. The neighborhood of 1 is just x. V is equal to x, and we can take whatever capital N we want. We can let n be 1. For all k greater than or equal to n, we have xk is inside v, because it's inside x. I'll write that the other way around. Okay, and that means that it does converge to 1. Okay, the second one's a bit more annoying. 1/2, 1/3, and so on with the cofinite topology. So for part 2, so with the standard topology, we suspect it converges to 0. So a good idea usually is just to test if this is true. And our topology right now is the cofinite topology. A way to think of the cofinite topology is it's the set of real numbers which we can draw as a number line, except for finitely many points. I don't really know how many, or like, it doesn't matter where they are, it doesn't matter how they're spaced, as long as there's finitely many. And let's just say 0 is here. Then no matter how many points, okay, my claim is that this sequence is always eventually inside any of these cofinite sets. The reason is because this can only exclude finitely many points. So for all v in the neighborhood of x, and right now it's in the neighborhood of 0, v complement has finitely many points. Okay, but since there's only finitely many, then that means it can't contain the entirety of our sequence. So that means xn is eventually not in v complement. You can make this more rigorous, but I won't do that here. But that means xn is eventually in v. And part of this is because, the reason why this is true is because xn has, it takes infinitely many values. So that means xn is eventually in v. And the next thing to notice now is, does it converge to anything else? Or like, that's what you think about next? And the answer is yes, because if you think about it, when did we actually use the fact that it's 0? Like, did it matter that it was 0? So we can actually replace this with just any number x, and we can take a neighborhood of x, and everything still holds. So actually what happens is, this sequence converges to every value in R. Okay, that's cool. Moving on. Okay, this one I'll work through a bit more quickly. The same sequence in R, but with a discrete topology. So remember, the discrete topology is just the power set of x. And one thing to notice is the smallest neighborhood of x is just the singleton. So I'll do this with 0 for now, so it's easier to follow. If I want my sequence to be eventually in this set, then that means it has to eventually be 0. And we can apply this to any real number we want. The smallest neighborhood of x is the singleton containing x. This does not converge to that. So I does not converge. And for II, again, we can think about each individual point. So for part 2, does it converge to A? Does it converge to B? Does it converge to C? So the smallest neighborhood of A is the singleton, but it's not eventually in here because there is always a B. So it doesn't converge here. But for B, well, the smallest open neighborhood is AB. And so this is going to work because the sequence is just in AB already. and C, the smallest open neighborhood is ABC. Our sequence is eventually in there. So this works. Okay, yeah, and that's what happened inside here. Okay, now continuity. Continuity, before it dealt with the metric, right? Before we dealt with like for all epsilon, we use epsilon delta essentially with the metrics, and we proved that a consequence of that was F inverse of an open set was open. Don't use this notation, by the way. It's just to explain what's happening. So we showed that this was equivalent to continuity on a metric space. But now with no metric space, that leaves us with this as a good definition. So this is now the definition for X tau, because now we do have the notion of open sets very naturally, but we don't have the notion of distance. Okay, suppose these are topological spaces. We have a continuous function. So continuous by definition, remember that means F inverse of an open set is open. And we want to check which of these is true. Okay, so obviously the second one's true, just by definition, because to be open means to be in the topology. And so if V is open, then F inverse of V is also going to be open. But the image of an open set is open is not actually always true. One way we can see this is, let's consider, so it's actually pretty easy if you consider different topologies. If we think about, at some point you would be introduced to the concept of fine and coarse topologies. So it's essentially how big or small the topology is. If I map from R to R, map X to X, but I use different topologies. So here I use the discrete topology, and here I use the standard topology. What will happen is, okay, we need to check it's continuous. It's continuous because if you think about what the discrete topology is, tau discrete is just a power set of X. So for every V in, I'm going to call it T2, tau 2. For all V in tau 2, V is also in the power set of X, kind of by definition, which is tau 1. But if I consider F of, let's say, the singleton set of 0, this is equal to just the singleton again, except this is open in tau 1, but not open in tau 2. Yep, so this just says continuity doesn't tell you anything about the image of open sets, only of the pre-image. Okay, Hausdorff topological spaces. Hausdorff, let's just see what it says. On a metric space, if X and Y are not the same point, then a metric should ensure that the distance between them is positive. How do we do this on a topology? Does it say here? Yes, it does. So for every pair of points that are distinct, then there are neighborhoods such that okay, there's open sets U and V such that X is in one neighborhood, Y is in the other neighborhood, but the intersection of them 0. So I used neighborhoods and open sets kind of interchangeably there, which you probably shouldn't do. But the idea is, if this is the topological space X, or this is the set X with a topology, then if this is X and this is Y, then I can always find sets like this. I can always find a U and a V, and let's do it like this. So X is in one of them, and it's in tau. Y is in another one, and it's in tau, but they do not overlap. So this is the same thing as with a metric, where if we had 2 points, you can always draw arbitrarily small balls around them. Or just balls small enough so that they don't intersect. Okay, and the good thing about Hausdorff spaces, this is actually very important, is that it gives us unique limits. And that's a nice exercise if you want to prove it yourself. Let x tau be a topological space, x dash tau dash be a Hausdorff topological space, and suppose f is continuous and injective. Okay, so important stuff here is the codomain is a Hausdorff topological space. We have a function that's continuous and injective. We want to prove that x is Hausdorff. Okay. So how should we prove this? So I want to prove that for all x, y in X, such that x is not y, I want to find open sets containing x and containing y that are distinct. Now let's write down what each of the things mean. Okay, so x dash tau dash is Hausdorff. That means for all x dash y dash in x dash, there exists u v in the topology such that x dash is in u dash, y dash is in v dash, but u dash intersect v dash is empty. So here's our space X, here's our space X dash. What happens is, let's say this is X, this is Y, this is X dash, this is Y dash. I don't know what's happening with X and Y right now, but what I know for X dash and Y dash is that I can find neighborhoods around them, or find open sets around them that are distinct. Since it's continuous, then I can, then the pre-image of every open set is open. So what that means is if I take the pre-image of this and the pre-image of this, they should also be open. And it's injective. So what injective means is that x not equal to y implies f of x is not equal to f of y. So what, hopefully you can see what happens now. Now we let x dash be f of x, y dash be f of y. We can find neighborhoods around them. So we can find u dash v dash in tau dash such that f of x is in u dash, f of y is in v dash, but u dash intersect v dash is the empty set. And now I can take the pre-image of these. Okay, and what do we need? We need these to be, we need x to be in u, which is true because f of x is in u dash. We need y to be in v, which is true because f of y is in v dash. And we need u intersect v to be at the empty set, which is true because f is injective. Right, so separate outputs have separate inputs. Cool. And yeah, then we're done. Okay, now we're going to talk about bases. Let's just skip to see what they have to say. Okay, so there's a bunch of ways to define a topology. For example, if we have this and we want a topology on it, then what we can have is the empty set x, y, and xy. But this is kind of the same thing as just x and y. Because to make a topology out of this, we need to be able to take finite intersections, which gives us the empty set, and take, oh, sorry. Sorry, okay. We can either take, take the intersection, which gives us the empty set, or the union, which gives us this, and that just, it kind of makes the same thing. So we want an idea of like how to generate a topology. So these are things we call bases, which are similar to like bases in vector spaces. They're kind of like the building blocks of the topology. So to make this rigorous, we have a thing called a base. Okay, well, I'll look at what a local base is first, because there's a... No, actually, let's just look at bases. So a base is a subset of tau, such that everything in tau is a union of elements in B. Okay, cool. And a local base, so if we have topological space X and a point X, then a local base is a set of open neighborhoods of X. So it's a set of open sets, such that you can think of it as it gets arbitrarily small. So in other words, if U is any neighborhood of X, so let's say this is U, then I can always find a small enough set in the local base, which for example would be this one. Okay, give the definition of a base for a topology, prove that this is a base. Okay, so I'll look at what we have in a couple slides first. These are two conditions for B to be a base. So these two conditions are, it needs to cover X. So that just means it's the union of everything in the base is X. And that if I have two things in B, then there's something else in B that's inside the intersection. Actually, no, it's slightly different. It's if you have a point inside the intersection, you can construct some element of B that's inside the intersection, and that contains X. So for every X in the intersection, there is something in the base, such that X is in the base, and such that X is in V, and V is inside the intersection completely. So for B, we kind of just need to test that those are true. So remember, the first thing is that it has to cover it, and the second thing is the thing with the intersections. I'll just label it as this. So for 1, I won't do this rigorously, but it should be easy to see. If we take all the open sets like this, okay, how about I write it like this? I take a plus 1, b plus 1 for all integers a and b. If I take the union of all of these, I can write it like this. The union of these actually no, this will miss some of the integer points. Let's make this 2. This should cover x, which is r squared. And then I want to show that if I have the intersection of two, okay, so these are really rectangles, right? With this as A, this as B, this as C, this is D. If you intersect two rectangles and you have a point here, you should be able to create a smaller rectangle. I won't do that here, but like hopefully it's easy to see how you can do that. You just find like this distance, this distance, this distance, this distance, and then make a small enough rectangle. What did they have to say here? Yep, so this is just explaining what's happening here. So the reason why these, this is enough to say B is a base of tau is just because if you have these conditions, then you're going to satisfy the conditions for a topological space once you take the set of the unions of these points. Okay, but we can go even smaller. We can introduce something called a subbase. So let's look. S is a subbase. If we can make a base out of any set by taking the set of finite intersections inside S. And you can easily check that this set satisfies these two conditions to be a base. And then we can generate tau from this. So it's like step 1, we have S. Step 2, generate the base. Step 3, generate tau. So tau of S is the topology. Okay, so yeah, they call this tau of S. Tau of S is a topology generated by S, and S generates tau. Okay. Yeah, so that's just what they said here. Yeah, and just another thing, this intersection includes the empty intersection. So this thing. Ooh. And so, yeah, the empty intersection is just the entire space X by convention. Okay, so now we're going to talk about convergence, convergence of functions. So we'll skip through this. We'll just look at what's happening here. We want to figure out how to encapsulate pointwise convergence. So we introduce something called a gate set. So what do you think about this is, if I have a set, so if I have a function like this, and I want to converge to it, then at every point, I want my output to be within epsilon of the actual output, okay? So that means we can make a set like this. which is the set of all functions that kind of pass through this window or this gate. So for example, this function would pass, this function would pass, this function would pass, and so on. You take the set of those. And with a topology, we talk about all neighborhoods, right? So you can have this gate anywhere and as tall as you want. So you could have it here and be like this tall, let's say. And then what happens is if a function, if a sequence of functions is always eventually in every single one of these gates, then it's going to converge pointwise. And that's the intuition behind it. Okay, yeah, so you can use this as the subbase and then generate a topology from it. And we call it T pointwise. And it actually happens that if you have pointwise convergence in like a normal sense, it corresponds to convergence in this topology. And that's also a nice exercise. Weak convergent is for Hilbert spaces. We say that a sequence of vectors converges weakly if for each vector in the Hilbert space, the dot product or the inner product converges to this inner product. So this is called a weak topology because it's weaker than convergence in the norm of the inner product space. And the way we do this here is to have this equivalent to convergence inside a topology. We use this. It's kind of similar to the gate sets we had before, except what's the best way to put this? So let's say we have an x here and we have a y here. Then if we place z somewhere, and let's also place the origin. So this is like, just think of this as y. Then the inner product of z minus x with y, you can think of this as, you can take the projection. Actually, let's put z somewhere else. This is z minus x. If you project this onto y and find the length of this thing, this is z minus x in a product with y over the size of y. And so you can see that if we have the gates, or I'll just call them gates, z minus x in a product with y less than epsilon, that kind of puts a restriction on how narrow this has to be. Okay, and the narrower this is, the closer z's going to have to be to x in this direction. So for small epsilon, it forces z to be somewhere within this region. And so if you do this for all y, because remember this has to be true for all y, then eventually that means that z is going to have to converge to x in some sense. And yeah, you can prove that the topology generated by this is the same thing. Convergence in that topology is equivalent to convergence in the weak sense. Okay, so now we can talk about nets. So a net is like a generalization. A net is a generalization of a function. Oh no, not of a function, of a sequence. Because with a sequence, it was very linear, right? If you have this, it's like x1, x2, x3, and so on. It's very linear. You need some like order in here, but sometimes you can't have that. So the way we do that is to introduce something called a net. So a net is a directed set with a binary relation satisfying. It's kind of like what you'd expect from less than or equal to. it's reflexive, transitive, and for any 2 points, there's a point larger than both. Okay, the way I think of a net is, so normally it'd be like just a straight line downwards, but now we can think of it as like a tree, where each thing like is bigger than something else. Just think of it as like do you remember Hass diagrams from partially ordered sets? Think about that, but it can get extremely big. And so what the third property says is if you take this point and this point, let's say, then you can like trace it up the tree and they have a common ancestor somewhere. Okay. And right now we can use an index set lambda. And lambda doesn't actually have to be countable. So this allows for a lot of shenanigans. Yeah, so a net is kind of like a sequence indexed by lambda. So that's what this means. And we have a definition for convergence inside a net. So x lambda converges to x if for all, okay, they have that here. For all v inside the neighborhood of x, there exists an alpha which can depend on v, such that if something's larger than alpha, then x lambda is inside the neighborhood. So it's the same thing as a normal sequence, except now it doesn't really, it's not necessary to have just a sequence, or to have like, to have every element be comparable. Okay, moving on from nets, there's a thing called homeomorphisms. Let's see. Yeah, so they just have the definition here. A homeomorphism between two spaces is a function such that both the function and its inverse are continuous. So remember, that means f being continuous means f inverse of an open set is open. F inverse being continuous means that f of an open set is open. So these are very nice. It means it preserves openness. And yeah, like kind of the motivation behind this is to preserve connectedness. Okay, and hopefully we'll get to that as well. Okay, this is dealing with compactness, so we can skip this for now because we haven't introduced compactness yet. But if you're interested, you can look at this question, I guess, and this would be the solution for it. Okay, so for this one, A, define what it means to be homeomorphic. Okay, I should probably introduce something, which is homeomorphisms. The important thing about them is that they preserve, or one of the important things is they preserve connected components. And in particular, another consequence of this is that if the function's from x to y, I'm going to use this notation. The amount of connected components of x equals to the amount of the connected components in y. And so that's important here because, okay, part A, I'm assuming we can do, it's just a definition. Part B, in the complex plane, the unit circle, it should not be homeomorphic to x squared minus y squared is 1. So that's going to be this rectangular hyperbola here. And the reason is because of a different amount of connected components. But here we clearly have 2. Okay, so that would be like the reason why. You can make that more rigorous, but I won't. And then part C, let omega be a continuous, the set of continuous functions from 1, 0, 1 with the uniform norm topology. And then we can define a set of functions which map a function to its function value at tau. At t. Let tau1 be the topology on y1 of pointwise convergence. Let y2 be 0, 1. Prove that y1 tau1 is homeomorphic to y2 equipped with its usual metric topology. Okay, so what you would have to do is you would need to find a function from from y1 to y2 such that f is continuous and f inverse is continuous. Okay. Unfortunately, we don't have much time, so I'm just going to leave this for now. We're just going to move on. Yeah, so here's the stuff with connectedness. Topological space is connected. Okay, so there was connected components before. I kind of introduced that very roughly, but now we can talk about connectedness in a very rigorous manner. So a topological space is connected if it's not the disjoint union of two disjoint non-empty open sets. So if this is our space and this is Y we're talking about, this is connected because if you try to make this as the union, well actually, right now we're just talking about the entire space. So let's say this is X. This is connected because no matter what, if you try to have two open sets like this, well, okay, there's going to be missing points here in the intersection if it is connected. Or if there are no missing points, then that means that these two things have to overlap. Okay, so connected means you can't put it as a union of disjoint non-empty open sets. Whereas if X is not connected, here's an example of that. Then this can be the first component, this can be the second component. Both of them are union, both of these are open sets. And they're non-empty, they're disjoint, but the union is the entirety of X. And then there's a proof that, there's a theorem that says that if you have a continuous function, then it preserves connectedness. So F preserves connectedness. And a corollary of this, or something equivalent to this, is that F inverse preserves non-connectedness. So hopefully you can see that if it's homeomorphic, so the function and its inverse are both continuous, then connectedness and non-connectedness are always preserved. We can also have path connectedness, which is to say that if I have a pair of points, so yeah, this is stronger than connectedness. If you pick any 2 points, then you can have a function such that f0 is here, f1 is here, and it's a continuous function from 0, 1 to x. So there exists a path between the 2 points. And yeah, you can prove that this implies connectedness. So here, there's a problem, part A is skipped. Prove that x, which is the real numbers except 0. I'll draw it like this. And r squared except 0 are not homeomorphic. Okay, why aren't they homeomorphic? Well, hopefully you remember, since homeomorphisms preserve connected components, then what's meant to happen is f inverse of y. Okay, so the proper answer would be something like this. Suppose there exists a homeomorphism f from x to y, then f inverse of y should be connected. But clearly x, which is f inverse of y, is not connected. Another way to think of this is this is made up of two components, but here there's only one big component. And then for part C, prove that r and r squared are not homeomorphic. This is a very nice, just slight modification. What you can do is, if you take all the real numbers and the entire r squared, it's still true that f inverse of open sets should be open. So if I take off this point, and let's say that x is f inverse of 0, 0, so something that maps to this point, let's say that's here, then if I extract out this point, then I extract out this point. But what happens is now f inverse of y minus 0, 0 should be open. Oh, sorry, should be connected. Because this region is connected. But clearly there are two components here. So it doesn't work out. Okay, cool. And that's the end of topological spaces. I'm going to hand off. And next person, we'll talk about compactness.
Okay, I'll get started with compactness. So compactness is a property of a topological space, or a subset of a topological space. But yeah, so compactness is a way to deal with the notion of finiteness. And it's to deal with open sets that like cover a set. That means the union of those sets like equals or is a superset of this set. So compactness is a way to kind of like deal with finiteness. It's a way to reduce infinite amount of open sets to like a finite amount for certain spaces. So we just head in with definitions. So okay, a topological space is compact if for every subset of the topology such that we have these things, such that like we have a cover for the space, there exists a finite subset of that cover such that it also covers the space X. So we can call this finite cover that's a subset of our possibly infinite one. We call it a subcover of this one. Yeah. Okay, and then a subset is compact if it is compact in a subspace topology. So what that will end up meaning is we can just use Y subset of the union. So here we have equals X if we want to replace that for whether a subset is compact, you can just write this, and this thing will just become superset Y. And that's basically taking out the intersection Y part out of the subspace topology definition. Okay, in other words, something is compact if every cover has a finite subcover. And this is an example of a compact interval in the reals, in the topology we're used to. Okay, here's some quick properties. So suppose we have a compact topological space. If we have a closed subset, then it is also compact. The reason being is that, say you have some cover, you can add Y complement to that open cover. If you have an open cover for Y, you can add Y complement to it, and then suddenly you have an open cover for X. You can use the fact that X is compact to get a finite subcover, and that should end up covering Y as well. As for this other thing, okay, suppose we have a Hausdorff topological space. If Y subset of X is a compact subset of X, then X is closed. So the reason being is because for each Y and Y complement, we want to try find an open ball around it because we're showing that the complement is open. So what you do is you consider pairs of disjoint neighborhoods of like elements X and Y and Y. We know such disjoint neighborhoods exist because of the Hausdorff property. You can like take the union of all those neighborhoods of X, and that should give you neighborhoods of points in Y. You take their they will end up covering Y. You can take a finite subcover, and then they should correspond to disjoint neighborhoods of Y. And you should be able to take the finite intersection of them to get an open neighborhood around Y. I believe that is the gist of the proof of that. Okay, so here's the theorem. Hein-Borel. A subset of Rn Euclidean space is compact if and only if it is closed and bounded. So closed and bounded and compact are equivalent in Rn. Okay, and then Bolzano-Weierstrass. Every bounded sequence of real numbers has a convergent subsequence. The proof for Bolzano-Weierstrass is pretty elementary. Use a simple argument. Okay, but then Bolzano-Weierstrass, you can extend it to show that every bounded sequence in Rn has a convergent subsequence. Because you apply the theorem to the first coordinate to get a sequence that's convergent in the first coordinate, and then, a subsequence, and then you take a subsequence of that to get one that's convergent in the first and the second, and so on, until n. Okay, a topological space is called sequentially compact if every sequence in X has a convergent subsequence. So the following things are equivalent for subsets of Rn. Being compact, being sequentially compact, and being closed and bounded. You can look up to the results from earlier. So Haring-Borel gives compact and closed and bounded are the same. So we have that these two things are equivalent by that. Not these last two things. The first and the last one. These two things are the same. And for sequentially compact, one way to think about it is, okay, let's say X is closed and bounded, and we have some sequence in X. Well, then the boundedness part of X being bounded is going to make that sequence bounded, and X being closed is going to mean that. Hang on, okay. X being bounded means the sequence is bounded. That sequence will contain will contain some convergent subsequence by Bolzano-Weierstrass, because we can apply that now that we have bounded. And then, so the limit of that is also going to be in X, because X is closed, so it contains its limit points. So that's why this will get you sequentially compact. And for the opposite, going in the opposite direction, can say that if X is sequentially compact, then can say that it should be bounded, because if it's not bounded, for every natural number n, you can just find some vector with norm greater than n, and so for each natural number you get an element, and that forms an unbounded sequence. So that should negate the idea of it being sequentially compact. Because that will definitely not contain any convergent subsequence, because it will diverge. And it should, X being sequentially compact should also imply closed, because you'll contain the limit point of the subsequence, and so it will contain all its limit points if X is sequentially compact. So that's how we kind of equate all those things. Okay, continuity over compact spaces. Let X and Y be topological spaces. If function from X to Y is continuous and X is compact, then fx, which is the image of x under f, is compact. Okay, so continuous functions map map compact subsets. Oh, sorry, we'll map the space, compact space to a compact subset. And you can reason that by, say you have an open cover of Y, you can take the pre-image of all those open sets, because continuity, the pre-images will be open, and then when you're back in X, you can apply the when you're back in X, you can use the fact that it's compact to get a finite subcover of X, and then the images of all those open sets will get you the finite subcover you want for Y. Okay, yep, so this is in fact 0, 1 is compact, and so is any closed interval in this form. Okay, if we take a continuous function from some interval to R, then the image is compact. And well, yeah, and so in terms of R, it also means closed and bounded. And so if it's closed and bounded, then it's going to contain a minimum and a maximum. So yeah, here's the maximum theorem, but it's maybe better known as the extreme value theorem. So suppose you have some continuous function like so, then it attains a maximum and minimum. Okay, continuity over compact spaces. Okay, recall that a function x to y over metric spaces is called uniformly continuous if for all epsilon greater than 0 there exists some delta that depends on epsilon, such that the distance of x and x prime being less than delta implies that the distance between f of x prime and f of x is less than epsilon. Here's another theorem. It's actually called the Hein-Cantor theorem, but it's not named in notes. Okay, let X be a compact metric space, and let F be a continuous function to the reals. Then F is uniformly continuous. And this result actually generalizes to any metric space, not just to R. Okay, problems. Okay, suppose we have x and x prime as topological spaces. So, prove that if y is a subset of x and is compact, and we have a continuous function from x to x prime, then the image of y is a compact subset of x prime. We kind of proved this already with one of the above results. We said that if the domain is compact, then the image is compact. Here we don't have that the domain is compact, because we don't have x is compact, but we have y as a compact subset of x. So we might as well just restrict x we might as well just restrict the function f to y, and then apply that theorem. But I think we do have a bit of a little further proof here, but it's similar to what I would have been saying earlier. Yep, so for any open cover, you can consider the inverse images, and yeah, it's going to be open because f is continuous, and these form an open cover of y, and then you use the compactness of y, and then take the images again, yeah, to get a new finite subcover. Okay, next question. Suppose that y prime is a compact subset of x prime, so this is in the co-domain, and that f from x to x prime is continuous. Is the inverse image, the pre-image of y prime, necessarily compact? And I argue that no, it's not. Because we can suppose that x is the reals and x prime is also the reals. And we just consider the zero map from the reals to itself, the map that maps everything to zero. So in that case, our y prime is just going to be 0, or the set containing just 0. And this is closed and bounded. It's obviously bounded. The reason why it's closed is because the complement, you can think of it as being open. So yeah, but then the inverse image of that is just the whole space, which is definitely not compact because it's unbounded. Yeah, just that. Okay, we consider a metric space, and we can talk about compactness on metric spaces by discussing concepts of boundedness. But here I introduce a bit of like a stronger form of boundedness. So a metric space is said to be totally bounded if for every epsilon greater than 0 there is a finite set in X such that X is a union of epsilon balls around those points. So okay, if a subset is totally bounded, then every subset is also totally bounded. And yeah, the closure of Y is also totally bounded. Okay, so suppose we have a metric space X. The following things are equivalent. X is compact. X is sequentially compact. This is for a metric space. And X is complete and totally bounded. Okay, in other words, every compact space is complete. Yeah, compact metric spaces are complete. But, okay, yeah, not all complete metric spaces are compact, because if you don't have the bounded or totally bounded property, then you fail to be compact. Essentially, for complete metric spaces, totally bounded and compact are equivalent. So yeah, as an example, like Euclidean space is complete, like R to the n, it's complete, but neither compact nor bounded. So you can see that they're sort of the same thing. Well, bounded, and if it's not bounded, it can't be totally bounded. Okay. Yeah, so complete metric spaces require total boundedness for them to be compact. Okay, suppose that x and y are two metric spaces. We now turn our eyes to sets of functions between these two spaces. So a subset S of continuous functions from x to y is said to be pointwise equicontinuous if, for every point x and epsilon greater than 0, there exists some delta that depends on both of them, such that for all the functions in this subset, we have that the distance between x prime and x being less than delta will imply this. Kind of similar to pointwise convergence, sort of, to the difference between that and uniform convergence. And it's also similar to pointwise continuous versus uniform continuous. Uniformly equicontinuous, if for every epsilon there exists a delta such that for all f in S, we have that that whenever x prime and x have distance less of delta, then f of x prime and f of x have distance less than epsilon. So yeah, similar to pointwise versus uniform convergence, pointwise depends on just the point. Specifically depends on the point, whereas uniform is something that must hold for all the points. Uniform equicontinuity is going to imply pointwise continuity just by using the epsilon you get from uniform equicontinuity for every x that you need for pointwise. But we can kind of equate pointwise and uniform equicontinuity when x is compact. Suppose x and y are metric spaces and x is compact. Then a subset of continuous functions from x to y is pointwise equicontinuous if and only if S is uniform continuous. So there'll be the same thing for a compact metric space. And we also have this Arzelà-Ascoli theorem. So a bounded subset of continuous 0,1 functions, the supremum norm is totally bounded if and only if it is equicontinuous. And apparently this holds for any compact metric space, not just 0,1. Okay, so this theorem implies that, subsets of continuous functions here is compact if and only if it's closed, bounded, and equicontinuous. Here, so we're also equating pointwise and uniform in this definition, because they'll be the same thing. Okay, Weierstrass approximation theorem. Here's something handy that will help us in the coming question. So think about this metric space with the supremum norm. The Weierstrass approximation theorem says that for a continuous function f on a closed and bounded interval ab, so basically an element of this, for any epsilon greater than 0, there exists a polynomial such that their distance with this norm is less than epsilon. So you can approximate such a continuous function on a closed interval arbitrarily well with a polynomial. Okay, here's a problem. Say we have this subset of continuous 0, 1 functions, or such functions that integrate to 0. And let P denote the set of polynomials which lie in V. Okay, first we're asked to give an example of a non-zero element of P. So just some polynomial that integrates to 0 from 0 to 1. So we can just take one that kind of looks like this. And that will so one that's like half underneath and half above the x-axis. So that ends up being what, x minus 1 on 2, I believe. Yeah, because if you integrate that, x squared minus x squared on 2 minus x on 2 from 0 to 1, that just gets you 0. Okay. Yeah, so we can just take x minus 1 and 2, clearly integrates to 0. Let's look at B. So what is the closure of P in this metric space? So because this is a subset of continuous 0, 1 functions, and it's quite a generous subset, because you think like, okay, no matter what a function in C0 to 1 integrates to, can always kind of like identify it with a function in V just by subtracting that integral from it. So there seems to be a lot of functions in V. And so we can hypothesize, because we also have our Weierstrass approximation theorem, which applies for limits with this norm, that the closure of P is just going to be V itself. That's what we hypothesize. So we can try to prove that. Yeah. So it's sensible to suspect that the closure of P will be V itself because of our approximation theorem. Okay. So we note that C01 is the set of continuous functions on the closed and bounded interval 0, 1. So yeah, approximation theorem applies for any function f in V. There is a polynomial P of x such that this holds. Notice how I put epsilon on 2 here. Maybe initially you first don't know that we'll have to do that divided by 2, but it should make sense because, okay, sadly we don't get P in V, but we might like to see how far its integral is from 0 and then possibly, subtract that from P to try to get something else in here. So maybe we need a bit more leeway than just epsilon. So we'll have epsilon and 2 here. Okay. So yeah, let's just integrate P from 0 to 1. I'll take the magnitude of that actually. So 0, 1 px dx. To try solve this, the only thing we know about it is how close it is to f. So might as well plus and subtract f. Px minus fx dx plus 0 to 1 fx dx. And then this thing is just going to cancel out because we know f, by definition of being in V, integrates to 0. Okay, and then can say that this is less than or equal to this. We can put the absolute value inside and make it less than or equal to. which is also less than or equal to the suprema of, well, like the greatest difference between f and p on this interval, which is this suprema norm itself times 0,11 dx, which is just less than epsilon 2, because this is just 1. So we do have some sort of bound on the integral of p, which is nice. It's pretty close to 0, but not exactly 0. But yeah, here's just the same working out there. Okay, so now we say that. Now we'll ask what happens if we just subtract the integral of p of x from it. We'll call it c. We'll call its integral from 0 to 1c. And then we now consider qx, which we define as px minus c. And now we know that this thing's going to integrate to 0. And because p is a polynomial and we've just subtracted a constant, q is going to be a polynomial as well. And then yeah, here's the actual like proper working out to see that q does in fact integrate to 0. So here we're just replacing q with what it's defined as. Separating this out, note that this is c already. So I just put the c here, and then this ends up becoming c as well. So it's just 0. Yeah, and then putting the things all together, we see that distance between f and q is this, and then by applying triangle inequality for norms, you can say that this is less than or equal to f minus p plus c. Maybe I should technically say c infinity here. Because it really is just like c minus the 0 function, or it's just a constant function. But yeah, ends up... I can just say, yeah, I can just have the norm of c, but that ends up just being c because what it really is just this. Well, the absolute value of c. And we know that is less than epsilon on 2 from the early calculation, and we started with this being less than epsilon on 2. You saw that was less than epsilon 2 anyway, so I can make this equality strict actually, and combine those two things together and say that it's less than epsilon. But that's exactly what we want to prove, because that will give us that p is dense in V, and so its closure will be V. Because what we're saying is that for any f, we can find a polynomial in V arbitrarily close to it. Okay, what was our question for C? Okay, yeah, is that complete? So, we know already, hopefully, that this metric space is already complete. And V is a subset of that under the same norm, so all it suffices to show is that it's closed, that it contains its limit points. But because V we already found was the closure of P, it is closed. Because the closure will just give you all the limit points. And you can't, applying closure twice has no effect. So yeah, V is its own closure and V is closed. Okay, so moving on to separation of points. Let x and y be two sets. A set of functions between x and y is said to separate points if for any distinct pair of points in x, there is a function such that it has different values for x and y. There's a function with different values of x and y. And here's another theorem. Let x be Hausdorff and compact. Then continuous functions from x to the reals separates points. Okay, here is a couple things that were hastily introduced, I think, at the end. So an algebra of functions is a vector space of functions. So, well, basically means you have addition and being able to scale it. This definitely is something that should make sense for functions that map to the reals. Okay, and then also close under pointwise multiplication of functions. That means multiplying functions by like fg of x equals f xg of x type of deal. Okay, and a unital algebra is an algebra that also contains the unit constant function 1. Okay, Stone-Weierstrass theorem. Let X be a Hausdorff and compact space. And suppose you have some subset of continuous functions from X to R. And suppose that is a unital algebra. Then A is dense with respect to this norm if and only if A separates points. So if we have some set of continuous functions and we know that they separate points because usually that tends to be easy to show, then we can say that that subset is dense with respect to this norm. And so we can find out things like its closure easily. Okay, so suppose S is the span of these functions. So x, simple exponential ones. Span is understood in terms of like linear combinations. So yeah, any function of the form like what, lambda 0 e to the 0. Oops, just lambda 0 plus lambda 1 e to the t plus lambda 2 to the 2t plus so on. Okay, that's what it's going to look like. Function that look like that. And we're asked what's the interior boundary and closure of S in the uniform norm, so that is this norm of continuous functions. That's our like underlying space. So okay, let's see if we can apply Stone-Weierstrass. So first we note that that this is Hausdorff and compact. Well, we can also look that here that X be Hausdorff and compact, and here we're thinking of functions from R to, oh, not from R to R, from 0, 1 to R. Okay, and this interval, closed interval, is going to be compact because closed and bounded, and also going to be Hausdorff because the reals are Hausdorff. Okay, also note that S is a unital subalgebra. So we'll go with unital first. It contains the function, contains the constant function 1 because we can just set all the lambda i's to 0 except this first one, which we can set to 1. So okay, we got that, and because we have the span of these functions, it'll be vector space, and in terms of multiplication, we can just say like, can just reduce it down to like e to the kt times e to the lt equals e to the k plus l t. So it like, which is still an element of S, and we can extend that to say that like it's fully closed under function multiplication. So that means we have an algebra, and because it has the unit, specifically a unital subalgebra. Okay, next we try to show that this separates points. So it's pretty simple. We can just take e to the kt, even just like e to the t suffices, and then take any two pair of points in 0, 1, because e to the t is injective. Then we can just apply, we know that e to the x is going to be not the same as e to the y. So these things are different when x and y are different. Otherwise, you'd have, well, you can just apply ln and get x equals y if they were equal. So yeah, so we know that S pretty clearly separates points. And so Stone-Weierstrass applies. So that will tell us that, S is dense in C01, well, with respect to this norm, which is what we are working with. And so the closure must definitely be C01. So it's the closure that we now have. We'll have that the interior is empty because we can just take any element of x. It's a function. It can also be arbitrarily approximated by a non-smooth but continuous function. So all the functions in S are going to be, should be smooth. But you can think of like a function that like kind of has sharp points. Shouldn't be in it. It is a bit of a shaky argument, but yeah, we should be able to find functions that aren't in S, but that are arbitrarily close to it. So we should say that the interior is empty. And then the boundary is just going to be C01, because we have this fact, just like by definition of closure, interior and boundary, that closure is the disjoint union of the interior and boundary. So if we have that the interior is empty, then the closure is just going to be the boundary. The boundary is just going to be the closure. Yeah, and that wraps us up. Wraps us up for this seminar.